Good. We're just coming to the end of the break. Hope people are fully refreshed and full of questions for the next set of presentations. I'm going to hand over to Zenwa to chair the next session.
Okay, thank you, Simon. So we'll start the second session of the team presentation. The first presenter is from CPQD UniCap. Flavio, can you share your screen now?
Can you hear me?
Yes, please go ahead.
Okay. And can you see my screen?
Yeah, yes.
Okay, just a minute. Okay, so hello everybody. My name is Flavio Simões, and I'm going to present the system implemented by CPQD and the University of Campinas for this challenge. We are identified as Team G, and this is a quick overview of our work. Our submission regards only to the hub task. Our system consists of a rule-based grapheme phoneme converter, a tachotron acoustic model, and a neural vocoder based on parallel waveguide. We have trained our system with data from multiple speakers speaking in 2 different languages. And we also have created specialized models to better handle non-declarative sentences such as questions and exclamations. Well, even though we possess a substantial amount of speech data in Spanish, we chose not to use this data for the challenge, okay? And the reason for that was that we saw this year's challenge as an opportunity to gather some knowledge about certain aspects of multilingual training. In particular, we were interested in learning the answer to the following questions. To what extent could a second language help in building a Spanish TTS, and how relevant would be the choice of this second language? So in our experiments, we compared 3 different settings. In the first one, we trained our model only with the Blizzard challenge data, which is European Spanish. In the second setting, we combined the Spanish data with additional data in English. And in the last setting, we combined Spanish and Brazilian Portuguese data. If we take a closer look at these languages, we can see that there is much more similarity between Spanish and Brazilian Portuguese. Most of the Spanish phonemes are also present in Portuguese, especially the vowels. And in the case of English, there is no such proximity. So we wanted to know if the acoustic model could benefit somehow from the similarity between the languages. And we designed our experiments to test that. So about the training data we used. For Spanish, we use only the Blizzard challenge data, which consists of 5 hours of a single female speaker speaking in European Spanish. In the case of English, we used a subset of Liberty TTS, consisting of 30 hours of 22 male and 42 female speakers. And for Portuguese, we used a proprietary data set that was originally built for unit selection synthesis, consisting of 30 hours of 2 male and 4 female speakers speaking Brazilian Portuguese. For data preparation, all audio files were split into segments of maximum 10 seconds. We converted all audio files to wave PCM at 22 kilohertz. Leading and trailing silence were normalized to a fixed length, and this DC level was removed. For text normalization, we used a proprietary tool to expand numbers, symbols, acronyms, etc. And for D2P, we also used a proprietary tool that is capable of handling all 3 languages using a common phoneme set. When training the acoustic model, the target language ID is informed by adding a tag with the language ID in the beginning of the D2P output string. For the speaker embedding, we use an external pre-trained network that computes the X vectors of the training data. So the mean X vector of a given speaker is added to the tachytron encoder output to inform the speaker identity. Well, we trained acoustic models for all the 3 settings described earlier and performed a subjective evaluation in the form of A/B tests in which participants listened to speech pairs from different models and indicated their preferences. As a result, we observed the preference for Spanish plus Portuguese model followed by the Spanish plus English, and then the Spanish only model. Well, an overall impression was that the Spanish only model resulted in audio with spectral noise and artifacts. The Spanish plus English model had a better audio quality, but suffered from flat prosody. And the Spanish plus Portuguese model had the best results. But, well, some considerations are important here. First, the difference between these models was not that large. Particularly, we observed that training only with the Spanish data resulted in highly intelligible speech. And, well, that was not totally expected, at least for us, from our previous experience with Brazilian Portuguese. 5 hours of speech was not sufficient to obtain intelligible speech. Pronunciation errors were not frequent in none of the setups, and we did not observe gross errors such as muffling, skipping, repetitions, and early stops. Well, given all that, we chose Spanish plus Portuguese as our final setup. And, well, all results presented from now on refer to this setup. In order to better fit the model to the target speaker's voice, we performed a fine-tuning stage in which additional training steps were executed using only the Spanish training data. The final quality we obtained was good, but we observed there was still some room for improvement, especially regarding the intonation of interrogative and exclamatory sentences, which did not sound very natural. So our proposition in this case was to create a specialized acoustic model for such sentences. What we did was to divide the non-declarative sentences into 4 categories: yes, no questions, in which the questions can be answered by a simple yes or no, or questions in which the question is posed as a choice between alternatives, open questions, which comprise all the remaining questions, and exclamations. So the idea here is to have a sentence classifier that decides what category the sentence belongs to in order to choose the appropriate acoustic model to be used. Sentences are classified by applying a set of rules, which are described in more detail in our paper. So the non-declarative models were obtained by fine-tuning the original models using only sentences belonging to the target category. Well, we can see that in the case of or questions and the exclamations, there are very few examples in the Blizzard dataset, which was not enough to build a good model for this sentence type. So we had to complement the fine-tuning data with sentences of the same category extracted from the Portuguese dataset. And, well, that worked fine. Regarding the neural vocoder, we used parallel wavegun, a single English female speaker model pre-trained with 3,000 case steps on the LJ speech dataset was used to initialize the network weights. Then the model was trained on the Spanish plus Portuguese datasets for 600 case steps. An additional fine-tuning stage was executed later using only the Spanish dataset for 900 case steps. In the end, the final network weights were obtained by averaging the weights obtained in training steps with the lowest validation loss error. Well, here are the results of the listening test conducted by the organizers. For naturalness, this is where we are. We achieved an MOS value of 3.55, while the MOS of natural speech is 4.21. Regarding similarity to the target speaker's voice, our mean value was 3.51, while the mean value of natural speech was 4.07. With respect to intelligibility, our word error rate was 17% for the SUS test and 4.1% for the Sharva test. In terms of statistical significance, these results are similar to most of the other participants. And particularly for the Sharva test, we can see that our word error rate is not significantly different from the error rate of natural speech as well. Well, here are some examples of our synthesized speech. This first example is for a declarative sentence. The following examples are examples of questions.
Sorry, I'm afraid we cannot hear your sample.
Excuse me?
We cannot hear your sample.
No? Sorry, I probably didn't share the other files.
You can read.
I will share. Or
Oh yeah, you can reshare your. Yeah, you can.
Okay, just a minute. How do I stop sharing? Okay, I start sharing sound. Can you hear now?
Ha sido un trabajo bastante complejo de
Yes, we can
desarrollar,
hear now.
pero también demasiado bonito de hacer.
Okay, so the first one is a declarative sentence. The following ones are questions.
¿Es una de esas personas que dicen siempre la verdad? ¿Quién va a hacer las preguntas? ¿Yo o usted? Si no le gustaban los juguetes, ¿por qué se iría con su peluche?
Okay, as a summary, we used a mixture of European Spanish and Brazilian Portuguese as our training data. We adopted some fine-tuning strategies for both the acoustic model and vocoder to improve the quality of the synthesized speech. We trained specialized models to improve the prosody of non-declarative sentences. Well, these strategies helped us place our system among the top-ranked systems in the challenge. Thank you very much for your attention. Happy to answer your questions.
Thank you. Any questions? You can use the raise your hand button, or you can type in your questions in the chat box or QA box. So I have one question regarding. Oh, yeah, we.
Yes.
Zhao, go ahead.
Hi.
Yeah.
I'd like to ask if you have any idea why did you get flat prosody when you trained with English together with Spanish? Because, yeah.
Yeah,
Thanks.
it was not exactly what we were expecting, but well, what I believe is that the prosody learned from English did not help model well the Spanish prosody, maybe because the languages are not so similar. That's my guess.
Thanks.
Okay. Any other questions? So I have one question. Did you try to use both the BP data and the AE data? I mean, use them together with the. I mean, use both the Portuguese and the American English data together.
No, we didn't do that. We didn't have enough time to do that. But
Okay.
well, for my guess, I think that would not help too much, because adding only the Portuguese data, we could get a quite good quality.
Yeah, I just want to make sure whether or not we need to select the language we used, or we can just put all the data available together. If the former is better, then we need to study how to select the most appropriate language for the training. Okay, thank you. I think the time is up now. Let's move to the next presenter. Thank you.
You're welcome.
The next presenter is from Trinity College Dublin. Zhao, please go ahead.
Yeah, I'm waiting. I'm waiting to be able to share the screen.
Yeah, okay.
Because because I cannot.
I can't find them. Okay.
Sorry, hello. I had to enable the video in Zoom, so I think I need to restart again the meeting.
Hello, Zhao, can you share the screen now? Okay. Okay, we can see that now. We cannot hear you.
Okay, is it okay now?
Okay,
Yeah,
yeah.
I'm sorry for this delay. I wasn't aware of the settings. My name is João Cabral, and I'm presenting the entry from Trinity College Dublin for the Blizzards. As our title suggests, in our work we kind of give emphasis to using the multi-speaker models that rely on using external data instead of building a speaker-dependent model for Spanish, using the shared data only. Yeah, so the motivations for our participation were to build a synthetic voice for Spanish for the first time and take part in this large-scale evaluation. We're also interested to address the challenge of code switching, which is the spoke task. Our approach was to use a non-autoregressive sequence model with multi-head attention, and this is a conformer-based fast speech to architecture. We used external data sets to deal with a small shared data set and no English data that was shared for the code switching task. We also tried to benefit from knowledge transfer in the form of transfer learning and multi-speaker modeling. So we chose the external data mainly because from our previous experience in building voice in other languages, you assume that you could get higher quality using a larger data set compared with the shared data set. However, we have not experimented to build synthetic voice with using the shared Spanish data only to verify the quality of a speaker-dependent model. The data sets that we used include the shared Spanish data set, approximately 5 hours, a subset of the Spanish ML Lab speech data set. For the task, it included 3 speakers, and the CSTR VCTK data set, which is an English multi-speaker corpus for the spoken task. We also use pre-trained models from start training voices for 2 tasks, as I'll give more details later. So our systems are derivations of the Fast Speech 2 and Transformer implementations based on ESP.NET2. The Transformer models were only trained to supply alignment information for training the Fast Speech 2 models. One of the differences that we use in our systems internal speaker embedding instead of relying on the externally supplied X factors. For the vocoder, we use parallel waveGAN trained on VCTK, a pre-trained model. And in the speech analysis, the record speech of the Blizzard Spanish dataset was downsampled to 24 kilohertz for compatibility with our pre-trained models. We extract F0 with DIO Puston mask algorithm, and the training criterion of our models is the sum of the spectral loss with pitch, energy, and duration losses. This table shows a summary of the main system configurations related to the encoder-decoder parts, the convolution layer, self-attention, and the embedding dimensions. So this figure shows different stages to build the Spanish synthetic voice from the pre-trained models and speech database in the up task. So in order to generate alignments for the Spanish speech data, we built a character-based speaker-independent transformer model on the MALab Spanish database. We start with this label subset, but we found that system did not generate good alignments. So our next attempt was to seed a transformer system with a multi-speaker Italian model that we trained in the past experiments. And interestingly, this succeeded in generating good alignments. So the resulting model was further adapted on the Blizzard dataset, and then these transformer models were used to generate the alignments on the Blizzard Spanish data, and as well to generate alignments for the MLab's Spanish data sets. So then on the aligned MLab Spanish data sets, we trained our initial character-based speaker-independent fast speech 2 model, which was warm start as well from a pre-trained MLab's Italian. So then the 5 best validate models are averaged and used as seeds for the model to be trained on an extended, on extended data sets consisting of the aligned MALab Spanish and the Blizzard aligned Spanish, so that to obtain then our final model that in which we adapt embeddings and train the model. So the choice of a speaker-independent model for a speaker-independent task may not seem obvious. So besides the motivation to use more data, we also aim to reuse the system built for this task as the seed model for the spoke task. Since our approach for the spoke task was to transfer speaker characteristics via the speaker embeddings, it made sense to start the final model from a already speaker-independent one. So that's what I'm describing now. For the spoke task, we built a speaker-independent fast speech 2 system with mixed character and phone token inputs. So we reused the aligned Spanish databases for the up task, these two, and added an existing pre-aligned VCTK corpus with phone tokens from the CMU pronunciation dictionary. Our character tokenization preserved word boundaries by inserting space tokens in contrast to the phone tokenization. And we also used a pre-trained English model to start training. And then we start training with embedding adaptations followed by the full network training. One aspect that we neglect to model was that our combined character and phone tokenization did not account for the overlap between the one-letter phone symbols and character. Yeah, so this obviously can create ambiguity that is hard to overcome and cause kind of mixed language pronunciation within words. As seen in previous other approaches that have been presented, we thought that there may be benefits to solve this problem in tying the input the token embeddings representation of the language when there is overlap, and then using a separate embedding layer to signal which language phonetics realization to use. But due to time constraints, we're not able to implement this. So in terms of the results in the task, in the Sharford intelligibility test, the difference in intelligibility between our system and our system is not statistically significant. In SUS intelligibility tests for systems were significantly better than our system, and unfortunately ranked in the bottom in mean opinion scores and similarity to the original speaker. And I'm going to play to show you why. Okay.
La expareja de Tom Cruise, que ha participado en una sesión gráfica para la edición australiana de Vogue, ha decidido compartir una de las instantáneas sin un solo retoque.
Yeah, so as you can see, in our system, I think the naturalness scores were also strongly penalized by synthetic speech having a flat prosody, and also the sound also not very natural, perhaps because of the vocoder. In the spoke task, our system also ranked low, and the quality of the synthesis voice was not natural enough because it was similar to the quality of the voice built for the hub task. Just show you an example.
La expareja de Tom Cruise, que ha participado en una sesión gráfica para la edición australiana de Vogue, ha decidido compartir una de las instantáneas sin un solo retoque.
Yeah, but sometimes, as you can see in this example,
La modelo californiana Cassie Jacobs, de 56 años, se ha convertido en una de las 6 finalistas para protagonizar la portada de la revista Sports Illustrated.
as you can see, sometimes the English words are not well pronounced.
La modelo
So there's plenty of discussion. So our low quality voices that we obtained wasn't expected for us because we built high quality voice on other languages using the fast speech-to system before. A difference to our previous experiments was that we built voices either from a single multi-speaker dataset or a single speaker dataset in the past. Whereas here we consecutively fine-tune models built on different multi-speaker datasets. We assumed that this process of fine-tuning the models was not optimal and ended up in a lower quality voice compared with previous voices we built. Other factors that might explain, we used a small number of speakers from the Spanish MLabs dataset, which could be a factor. Other factor would be that models could have been overtrained to optimize speaker embeddings and resulting in worse, for example, in the pitch modeling. And in terms of tuning the system, we also did not do any hyperparameter optimization to find settings appropriate to the specific conditions. The result is non-intuitive for us because the validation losses of our models are around 20-25% lower than those of the reference models for ESP.NET Fast Speech 2 trained on VCTK. And since we use the same vocoder as this implementation on Fast Speech 2 trained on VCTK, there may be perhaps a mismatch between our synthesizer outputs and inputs required by the vocoder. So maybe a purpose trained vocoder would have yield better results. But we need to conduct further analysis to better understand the reasons for the results, for the result of lower quality. So in summary, one lesson learned is that using high quality and robust CNN-based system may not always yield a good result. In this work, all our models represent first attempts in each stage of model building, which may not be the best models that you can be achieved with this system. We chose the approach of building multi-speaker models instead of single speaker ones. One reason was to take advantage of much larger multi-speaker data sets. And the other reason was to be able to synthesize the voice of the target Spanish speaker for the model trained for a mix of English and Spanish speakers. We used a simple approach in the spoke task by using a different tokenizer for the Spanish and English text processing. And the evaluation results were lower than our expectations, but the participation was valuable for us in terms of what we learn and what we can learn more by investigating deeper the problems with this case study. Yeah, thank you for your attention.
Thank you. Since we are a little bit delayed, so I'm afraid we don't have time for answering questions. If you have any question, you can type in the QA or chat box. The presenter can reply them later. So
Okay.
Let's move to the next presenter, Yitao Yang from South China University of Technology.
Okay, I'm sharing my screen.
Okay, please.
Okay, can you see my screen?
Yes, we can see.
Okay. So, my name is Yang Yitao. I'm from South China University of Technology, and it's my great honor to present you this SCUT text-to-speech system for the research range 2021. So first, we had to talking about the tests. We work for this challenge. We select the sport test to build a code switch text-to-speech synthesis system for European Spanish and English. So as we know, most of the current speech synthesis systems are based on the data driving methods. So we need to, before we're talking about our system, we need to see what the data set we use. So we collect data from 4 data sets, including English and Spanish. So we can see this data set actually contains many speakers, and there are many compounds. And the biggest problem is that we only had monolingual data sets, and we need to build a code switch synthesis systems. So next, I will introduce our overall architecture, and the front-end module is the key module we apply to train the code switch synthesis, and we use the use an language independent uniform phony representation based on the phonological feature to and then is our textual tool based acoustic model, and we add our relational local encoder as a style encoder to balance the style difference between the different data sets, and we add a one-hot speaker embedding for the multi-speaker scenarios. But finally, we use widely used multi-band waveform and recorder to resort the waveform from the melt spectrogram. So let's give some details about our front-end processing, because we use it to train the code switch synthesis. As we know, one way to train the bilingual synthesis using only monolingual dataset is to use a language-independent linguistic feature, and the feature we use in our system is based on the phonological feature, which is derived from the International Phonetic Alphabet. We call IPA in here, and in the IPA, it's some phonological characteristics such as whether it is vowels or consonant, whether it was of the phonemes of the vowels or the openness of the vowels, etc. So each language can be converted to the IPA, and then the corresponding phonological feature can be found from the IPA chart. So we can use a binary vector to represent it, and this is our language independent representations. So and this table is the all of the classes of the phonological feature we use in our system. We can according to these categories of this feature, we manually mark the phonological feature for each Spanish and the English phony by considering the Spanish and the English IPA charts. So our front-end processing is that for Spanish or English tests, we first use the eSpeak NG tools to convert them into IPA, and then we find the phonological representations from the table we construct, and then to form the binary vector as the linguist representation. Next is the training state of our acoustic model. In order to balance the style difference between the several datasets, we use a VAE-based reference encoder to extract the style information, and for the of course the corresponding speaker one hop identification to indicate the speaker is also used. And these features are input together into the text control model with the linguistic feature we extract based on the phonological binary vector. But when it comes to the inference state, something is different. Since finally we want to generate the voice of the speaker in the Bc2021 2021 provided dataset. So for the style feature part, we need to remove the VAE encode and use a range style embedding among the Bc 2021 Spanish datasets, and of course the speaker embedding. The speaker embedding should be the Bc 2021 speaker. And the biggest difference is that in the during the inference stage, we need to end a language in the identification module, because we had to identify the Spanish and English words and translate the two part words into IP8. So we use the English and the Spanish dictionaries to distinguish between these two words, and our principle is that when the Spanish words take the precedence, it means that one word will be marked as an English word when it only appears in the English dictionary and not in the Spanish dictionary, because we believe the native Spanish speaker will tend to use Spanish to pronounce words that exist in both Spanish and English. Here are some demos. The first two sentences is the code switch tests can hear.
No quiere añadir nada antes de que el jurado se retire.
So the Greek word is the English word in these sentences, or can listen.
Retire.
It's not good actually. And the second one.
La vi hace 2 meses en el Teatro Grand en Woolwich.
This one is better.
Woolwich.
And next two sentences, this agreeing word actually it exists in both Spanish and English dictionary, but we think the Spanish words should take in our precedence. So this two word we still pronounce it as a Spanish word.
Ambiente ideal para tomar el vermú antes de comer. Ideal.
It's too soft.
Es una calle comercial del casco antiguo de la ciudad. Calle.
So in terms of the naturalness of the code switch acceptability of the similarity to the original speaker, we are in the median of all the participants. So finally, I will give some conclusions and discussion about our systems. We think our synthesis system can generate understandable speech and the phonological fountain, thus made the system capable of the code switch synthesis. But as we can see, the performance is lower than expected. So we think they may has two reasons. One is that our language in identification is very crude, and we didn't consider the actual semantic meaning of the bilingual tests. And finally, due to the lack of the native Spanish speaker or someone who are familiar with the Spanish in our teams, it also makes it difficult for us to evaluate and improve our systems. So I think this is all of my presentation. Do you have any question?
Thank you. Any questions? So I have one question. So you used the VAE in your model. So have you compared how it contributes to the final performance of your system? Because you just use the mean, the average of the embeddings, right?
Yes.
At the inference stage. You did not predict make any predictions. So I'm wondering whether or not the VAE can contribute to the performance.
Actually, during our training, the VAE is suffering from the vanish problem. So actually, I think the VAE encoder in our system didn't work as expected. So it also caused some problems because actually we inputted two types of additional feature to the texture model, like in this slide, the style feature and the speaker feature. When the style feature is unusable, so the speaker embedding is not only a speaker indicate, it is also a style of a dataset indicates. So when we finally generate the code switch, sentences, we use the Bc2021, the speaker embedding. So it may involve some Spanish Asian into the English words. So it makes it not natural enough or unacceptable.
Okay, I think the time is up now. Thank you, Yitao. Let's move to the next presenter.
Okay, I'll stop sharing.
Okay. The next presenter is Dan Wells from University of Edinburgh.
Yeah, hi. Share my screen. Okay, can we see this?
Yes.
Cool. Right, yeah, so I'm going to present CSTR's entry to the Blizzard Challenge this year. We focused on the spoke task, so synthesizing Spanish utterances, including some English words. And for this, I guess we had two main considerations. We wanted to train using both Spanish and English data. So we want to find some way to encourage some kind of information sharing across those two languages. And then also in the test utterances, when we come to an English word, we kind of want to think how should we generate an appropriate pronunciation for those words, which might involve some adjustment from the English pronunciation into Spanish phonology. And so as well as the system we submitted, we did some kind of additional evaluation of these strategies, which I think might be useful for approaches to code switching TTS in general. So just a quick overview of the model that we submitted. So this was based on fast pitch. We trained with multiple speakers. So because of the explicit iteration predictor, of course, we need forced alignments. We just used the Montreal forced aligner for this. And to this model, we add word level language embeddings to kind of capture any shifts between Spanish and English. Our training data is all monolingual corpora in the two languages, so we kind of keep that constant throughout an utterance during training. But for the test utterances, we come up with some automatic language ID procedure to set that word by word as we go through. And then for the audio generation, we use a waveGlow vocoder. We fine-tuned a pre-trained LJ speech model, which seemed to struggle with the trills in Spanish, trill the R. So we fine-tuned that with the Blizzard speaker data only. So an overview of all the data that we used. Of course, we start with the Blizzard data, and to kind of help with our forced alignments, we trimmed the leading and trailing silences on each utterance to consistently half a second. Then we have this L2 Arctic data. So this is second language speakers of English, and we selected 2 female speakers whose native language is Spanish. So this kind of gives us some Spanish accented English to work with. Then we sample a subset from LJ speech to get also some native American English. And then to add really some diversity to the Spanish data, we also sampled some audio from Mozilla Common Voice. So this is kind of crowdsourced data, some of which has accent labels. So we take only the matching kind of peninsular Spanish data, filter out anything that's was obviously low quality from a small sample. A lot of the text prompts here are scraped from Wikipedia. So again, checking kind of a sample of 500 utterances, we found maybe 10% of those contain some English words, mostly proper nouns, but not exclusively. And overall, that might be around 2% of the total tokens. So this maybe gives us, you know, at least some exposure to English as spoken by Spanish speakers. Additionally, we found really the addition of this large number of extra Spanish speakers helped our model to maintain the target Blizzard speaker's identity when we switched into English. You know, kind of helped us tease apart the speaker and the language here. Okay, so that's our training data. As I say, we're using both English and Spanish, and so we wanted some way of learning representations across both languages. And for this, we, similar to the previous presentation, we represent our phones as vectors of distinctive phonological features. So rather than having these kind of partially overlapping phone sets, we have a shared set of 25 features which are common to both languages. And this really allows us to have kind of direct parameter sharing between closely related sounds, even if they only occur in one language or the other. So for example, this ch occurs in both English and Spanish, but these other sounds which have nearly identical phonological feature vectors only occur in the English, but still we can capture that similarity. So for the conversion from phones to phonological features, we use this pre-existing panphon library, which has a couple of issues. So the trill and the tap R, which are distinct phonemes in Spanish, have identical feature vectors here. So we kind of fail to make some distinctions there. And this also doesn't have any lexical stress features. Okay, so that kind of gets us information sharing across the 2 languages, but at test time, as I mentioned before, we kind of want to know whether we're dealing with an English or a Spanish word at any given moment. So we came up with this procedure for automatic language ID. To start with, we feed the test utterances into a multilingual BERT model. So this is trained on the LinCE English-Spanish code switching corpus. And for each word in the utterance, this will tell us whether this will classify either as English, Spanish, or as a named entity. Turns out a lot of the English words end up tagged as named entities, in which case we have to do some additional disambiguation. So first we check for these Spanish specific characters. If we find any, then we say that's Spanish. If not, then we fall back another n-gram character model just to do that final piece of disambiguation. And to evaluate this, we kind of manually annotated 40 of the Blizzard test utterances for word level language ID. And we see overall we got around 95% accuracy, but only 17.5% of those words in those utterances were actually English. And for the English words, we have much lower accuracy. So this isn't perfect by any means, but it gets us some of the way there. And so as well as kind of driving the choice of language embedding in the test utterances, that also those automatically determined language labels tell us how we should generate a pronunciation for the word in question. So if we've decided this is Spanish, we run it through our own rule-based Spanish G2P. If we tagged it as English, then first we get a native American English pronunciation from a Combilex lexicon or G2P. And then we apply some nativization rules to map that native English pronunciation into more appropriate Spanish phonology. So for example, adding this epenthetic E at the beginning of words that start with S and a couple of other things. But we do maintain some English features. So for example, the kind of approximate rhotic R, we don't map that to a tap or a trill in Spanish. And we also maintain a lot of word final consonant clusters, which don't generally occur very often in Spanish, but we keep those in our English words, because otherwise we found it kind of goes too far from the original pronunciation if we just reduce those. So here's just an overview of the spoke task evaluation, the Blizzard evaluation. I won't linger here. This is just kind of to situate us where our system was system H, and we're kind of bang in the middle for the mean opinion scores and the acceptability of our English word pronunciations. So really, I'll move on to kind of our supplementary listening tests. So we did some additional, more explicit experimentation with comparing phone and phonological feature-based systems, and also a range of different nativization strategies. So kind of ranging from most closest to English pronunciation and then most Spanish pronunciation. We have this mixed nativization strategy. So this determines the pronunciations in the way that I described before. And again, uses the word level Spanish or English embeddings, depending on language embeddings, depending on which language we detect. This is kind of like an oracle version of the system that we submitted to the Blizzard evaluation, because we're just using these 40 utterances that we manually annotated. Then this nativized strategy, the pronunciations are generated in the same way, but we use a constant Spanish language embedding through the whole utterance. So this is maybe adding more of a Spanish accent to even the English words. And then finally, this Spanish is really not very much nativization at all. So we kind of apply a Spanish G2P naively to every word in the utterance, even if it's an English word. And then again, we have a constant Spanish language embedding. So we ran this listening test with 40 native Spanish speakers located in Spain online. We presented each sample along with its transcription with the English words highlighted, just to make sure listeners could focus on those. And then we asked for responses to these three statements. So whether they agree the phrase is very natural or not. Considering the English words, does the speaker seem to have good knowledge of English? And then do the pronunciations of the English words that we've generated match how the listener would pronounce them? So to summarize the Naturalness results, for systems using phones and phonological features, we saw no significant difference between those input methods for systems using the same nativization strategy, so kind of these pairwise comparisons, probably because the nativization removes most of the English phones from the input, but we found that in our kind of initial development to be beneficial, so we kind of ran with that. And then there's quite low correlation between these responses to the first question and the other two, which suggests that listeners are evaluating the whole sentence for naturalness and not just focusing on the English words. So if I play a couple of samples here, I'll start with the reference from the challenge.
Inhibit face and neck lift, el lifting de cabina definitivo para rostro, cuello y escote.
That's how it should have sounded, and then I'll just pick one of our systems.
Inhibit face and neck lift, el lifting de cabina definitivo para rostro, cuello y escote.
So this one scored an overall average naturalness rating of 2.5 in our evaluation, but 4.0 for knowledge of English and similarity of pronunciation to the listeners. So that kind of shows that, you know, the quality of the Spanish kind of matrix sentence is important for this. The main issue here was kind of unnatural intonation, and then also this this R here highlighted in red should have been produced as a trill, but we pronounced it as a tap. Then for the evaluating the English pronunciation, we found that this kind of naive non-nativization strategies, so just using the Spanish G2P, gave significantly lower naturalness ratings. Oh no, significantly lower ratings for both of these questions compared to the others. So some nativization seems to help in all cases, and the responses to these two questions were very highly correlated. Were quite highly correlated. So listeners' pronunciations tend to align with what they consider to be knowledgeable English. But they can still distinguish mismatches in particular cases. But I think I'm pushed for time, so I'll skip those things. Or maybe I'll skip the summary actually. So again, I'll play the reference here so we know how this should sound.
Y no es tanto spoiler como motor obvio y auténtico sentido de la película.
And one of our systems.
Y no es tanto spoiler como motor obvio y auténtico sentido de la película.
So this is kind of the system where we didn't adjust this pronunciation, right? This is just from Spanish G2P. But this word spoiler happens to be has been found to be a common loan word in everyday Spanish. So this kind of received a score of 3 on the English knowledge, but 3.8 on the pronunciation similarity. So you know, this is a case where, because this is a common loan word, listeners expect a more Spanish pronunciation. They don't necessarily expect this to be pronounced as English. Okay, and I'll wrap up there, sorry. Thank you. Any questions?
Okay, thank you. Since we are far behind the schedule, I'm afraid we don't have time for online questions now. If you have any question, you can type into the QA box or chat box, and the presenter will answer them later. So let's move to the last presenter of this section, that is from the Samsung Research China, Beijing, Chunhui Lu, please.
Can you hear me?
Yes, you can share your screen now.
Can you see it? Hi everyone, I'm Chunhui Lu from Samsung Research China, Beijing Speech Lab. I'm going to present our TTS system for Blizzard Challenge 2021. My presentation will be in 4 parts. First, a brief introduction. There are two tests in this year's challenge, hub test and spot test. We participated in both tests. We noticed the English words in spot test was expected to carry Spanish accent. So our strategy was first to convert them to English phonemes, then map them to their Spanish counterparts so that we can only build one system for both tests. When building the system, we only use officially provided 5 hours data. Next, I'll describe our system in detail. Here is an overview of our workflow. It mainly includes 3 stages: data processing, model training, and synthesis. First, in data processing, we downsample the audio files and extract male spectrogram. To generate phoneme sequence, we used an internal G2P module. It was a letter to sound model based on text. Then we used MFA toolkit and their open source models to do forced alignment. From the alignment results, we derived phoneme duration labels, and according to the silence duration after each word, we annotated the prosodic boundary of that word at one of 3 levels: no breath, short breath, or long breath. After data processing, we trained several data-driven models using processed data. First, breath predictor. It predicts the prosodic boundary type of each word from text. For this job, we took 2 open source pre-trained bird models, one for Spanish text and one for multilingual text. We fine-tuned both models on challenge scripts to predict prepared breath labels. The next one is acoustic model. It converts a phoneme sequence to male spectrogram. We built it based on a variety of fast speech, as shown in the figure. We augment the basic fast speech model by introducing phoneme level latent variables to capture local prosodic variations. The latent code was learned with VE framework. A reference encoder compute a variational posterior of the latents from phoneme-aligned spectrogram, from which we draw a latent code and join it with the main fast speech at encoder output. After this enhanced fast speech model was trained, we use the reference encoder to collect mean latent code for every phoneme in corpus and train a separate total predictor to predict it from text input under MSE loss. This total predictor was later used to provide latent code during the inference. For vocoder, we use -n to reconstruct the speech waveform. The model was first trained using direct truth spectrogram and then further fine-tuned using spectrogram predicted from an acoustic model to make up for the mismatch between training and inference. We only trained one acoustic model and one vocoder. They were shared by 2 tasks. Finally, in synthesis stage, we trained up all modules into a pipeline for text-to-speech generation. The text analyzer convert input text to a sequence of Spanish phonemes with breath markers. It includes 2 functions, G2P conversion and breath prediction. For breath prediction, we use birth ES for hub test and birth ML for spot test. For G2P conversion in hub test, we use previously mentioned internal Spanish G2P module. And in spot test, we first identified the English word from Spanish words using an open source language identification model. G2P for Spanish words was the same as in half task for English words. We first stated English G2P results, then mapped them to Spanish phonemes. The mapping rule was composed by informal comparing the full size of the two languages and listening to small task speech examples. That's all about our system. Here is the evaluation results. Our system performed well by most of the criteria. That validates the effectiveness of our method. In conclusion, we developed a system for both tasks, which featured a test analyzer, acoustic model, and a vocoder web pipeline. The test analyzer was task dependent and convert input text to a sequence of phoneme Spanish to a sequence of Spanish phonemes with prosodic boundaries. The acoustic model was built based on fast speech with phoneme level prosodic features augmented. For vocoder, we use HiFi to reconstruct the waveform audio. That's all. Thank you.
Thank you. So, any questions? So, Simon, please go ahead.
Hi, thank you for that. I have a question about you're using a kind of unsupervised per phone, what you're calling a prosody embedding, which you're getting from the spectrogram at training time, and then you're predicting from the phones at inference time. What do you think it's actually representing?
Actually, this what is a simplified version of our previous word. From the previous word, we find the latent code whose unsupervisedly learned some acoustic meaningful features, for example, energy and pitch.
Right. Are you not also predicting those separately as well? Or is this instead of what fast pitch and so on normally does?
Could you repeat it?
So are you also making an explicit prediction of F0 or energy, or are you only using this embedding?
Only use this embedding. It's learned unsupervisedly.
Okay, so it's instead of an explicit F0 prediction.
Yes.
Got it.
So, any other questions? So I have one question. You said you built the break predictor. So I'm wondering how did you get the training data for the break predictor? Do you label the training set or get the data from other resources?
We get the break label from the false alignment results. We according to the silence duration among each word.
Okay, you use the silence position as the position of breaks. Okay, I see. Okay, any other questions? If no more questions, let's thanks presenter, and this is the end of this blog. I'm afraid we don't have much time to move to the next session. So maybe only we just continue with the.
I was going to suggest we do take a small break because
okay, maybe we can have 5 minutes or
we take 5 minutes.
5 minutes. Okay, let's put off the remaining presentation 5 minutes later. Yeah. Okay.
Yeah. So the next session starts in 5 minutes. So do take a break because it's a marathon.
Yeah. Okay.